Hey everyone and welcome. So, have you ever really thought about what a falling apple and the moon orbiting the Earth could possibly have in common? I mean, one plummets to the ground, the other just hangs up there. Well, it's a question that completely changed how we see the universe. Today, we are diving deep into the force that runs the whole show, from falling fruit to the incredible dance of galaxies. We're talking about gravitation.
So this is the exact question that the one and only Sir Isaac Newton supposedly asked himself. He's watching an apple fall straight down, right? Then he looks up at the moon, which seems to just float. And that's when he had this incredible aha moment. They're both being pulled by the exact same force. The moon is in fact constantly falling towards the Earth. The only difference is it has so much sideways speed that it continuously misses us, getting locked into what we call a stable orbit. It's falling, but it never hits. Amazing, right?
Okay, so how did Newton actually describe this universal force? How did he put it into words, or better yet, into math? Let's take a look at the law he came up with, a rule that works for absolutely everything, from apples to entire asteroids.
You know, the really beautiful thing about Newton's big idea is just how simple it is. He basically said that every single speck of matter in the universe is pulling on every other speck of matter. That means you and the screen you're watching this on are gravitationally attracted to each other. It's just that the pull is tiny. But the Earth and the Sun, oh yeah, they're pulling on each other hard. If it has mass, it's in on this cosmic tug-of-war.
And this is the code. This is the mathematical sentence that describes that universal pull. This is Newton's law of universal gravitation. It might look pretty simple, but don't let that fool you. This little equation is the key to calculating the gravitational force between any two things in the entire cosmos.
So let's break this down piece by piece. The force, that's F, depends on a couple of really key things. First, the masses of the objects, m1 and m2. The bigger the masses, the stronger the pull. That makes sense. But second, and this is the really cool part, is the distance between them, r. The force weakens by the square of the distance. So what does that mean? If you double the distance between two things, the force doesn't get 2 times weaker, it gets 4 times weaker. Triple the distance, it gets 9 times weaker. This inverse square law is a huge deal in physics.
Now what about that g in the formula? Well, g is the universal gravitational constant. It's basically the universe's own tuning knob that sets the strength of gravity. And just look at how incredibly tiny that number is. That 10 to the power of -11. That's why you don't feel the gravitational pull from your chair or the person sitting next to you. The force is there, for sure, but you really need something with the mass of a planet for it to become a big deal.
Okay, so we've got the big universal law down. Now, let's zoom back in, right here to our home planet. We're going to see how gravity works specifically on Earth, and, more importantly, how we use that knowledge to get satellites up into space and keep them there.
We all learn in school that g, the acceleration due to gravity, is a constant, right? 9.8 meters per second squared. Well, that's not exactly the whole story. As you can see here, g actually gets weaker the higher up you go. That makes sense. But here's the part that might surprise you. It also gets weaker as you go deeper into the Earth. And why is that? Well, because as you go down, some of the Earth's mass is now above you, and it starts pulling you back up, canceling out some of the pull from below.
This graph just lays it all out perfectly. If you start at the very center of the Earth, the value of g increases in a perfectly straight line until you hit the surface. That's where gravity is strongest. Then, as soon as you move away from the surface, either up into the sky or away into space, that force starts to drop off, and it follows that famous inverse square law that we talked about earlier. So how do we get a satellite to stay up there? Well, it's all about hitting that just right horizontal speed. We call it orbital velocity. It's kind of like the Goldilocks speed, not so slow that it crashes back down, and not so fast that it just flies off into space forever. It's that perfect balance where it just keeps falling around the Earth, constantly missing it.
But what if you want to fly off into space forever? What if you don't want to come back? For that, you need something called escape velocity. You can think of it as buying a one-way ticket off the planet. If you can get your rocket going this fast, you have enough energy to completely overcome Earth's gravitational pull and head out into the great unknown.
Okay, let's put these side by side, because you will see this again. Orbital velocity, VC, keeps you circling. Escape velocity, VE, lets you leave for good. And for anyone studying for an exam like NEET, here is the golden nugget you need to remember. The escape velocity is just the orbital velocity multiplied by the square root of 2.
It's a super handy little formula that connects these two big ideas.
And this diagram shows what it all looks like in practice. A satellite's path is all about its speed. If you hit that orbital velocity perfectly, you get a nice, stable circle. Go a little bit faster, and the orbit stretches out into an ellipse. If you manage to hit escape velocity, your path becomes a parabola. You're not coming back. And if you go even faster than that, you're on a hyperbolic path, escaping Earth's gravity with energy to spare.
All right, let's zoom way out now, from satellites around the Earth to the scale of the entire solar system. Long before Newton explained why the planets move the way they do, an astronomer named Johannes Kepler figured out how they move. He came up with a set of laws that perfectly describe this cosmic dance. And Newton's law of gravity provides the physics that makes it all work.
So Kepler's first law was a huge deal because it corrected a belief people had held for centuries. Planetary orbits are not perfect circles. They're actually ellipses, kind of like squashed circles. And the sun isn't sitting right in the middle. It's at one of two special points inside the ellipse called the foci.
Kepler's second law is all about a planet's speed. Now, the official definition sounds a bit tricky, but what it boils down to is this. A planet speeds up as it gets closer to the sun and slows down as it gets farther away. That's it. This is why planets travel fastest when they're at their closest point, the perihelion, and slowest when they're at their farthest point, the aphelion.
And finally, Kepler's third law gives us this beautiful relationship between a planet's year, its orbital period, t, and its distance from the sun, r. It says the square of the period is proportional to the cube of its average distance. In plain English, the farther out a planet is, the way longer its year is, and not just because it has a bigger circle to trace, but because it's also moving much more slowly.
All right, we've gone through the story of gravity. Now, let's get tactical. For all of you gearing up for exams like the NEET, this next part is your gravitation cheat sheet. We're going to quickly run through the must-know formulas for satellites and their energy. Pay close attention here.
First up, potential energy. This is the stored energy a satellite has just by being in Earth's gravitational field. And the number one most important thing you have to notice is that negative sign. It is not a typo. That negative sign means the satellite is bound to the Earth. It's stuck in what we call a gravity well, and it doesn't have enough energy to get out on its own. Next is kinetic energy. This one's easy. It's the energy of motion, so it's always positive. Now, take a close look at the formula. See how similar it looks to the potential energy one? The only real differences are that it's positive and it's got that 2 in the denominator.
So what happens when you add them together? You get the total energy. And when you do the math, you get this formula. And look at that. Just like potential energy, the total energy of an orbiting satellite is also negative. This is the ultimate proof that it's a gravitationally bound system. It's not going anywhere.
Okay, now this table, this is pure gold for solving problems quickly. It summarizes the powerful relationships between all these energies. For example, look at this. The kinetic energy is just the negative of the total energy. And the potential energy is always exactly double the total energy. Memorizing these little shortcuts will let you fly through those satellite problems on your exam. This is a game changer. So, we'll leave you with one final, kind of mind-blowing thought. Of the 4 fundamental forces of nature, gravity is, by a long shot, the weakest. I mean, a tiny little fridge magnet can overcome the entire gravitational pull of planet Earth to hold up a piece of paper. And yet, gravity is the force that builds planets, that ignites stars, and that shapes entire galaxies. So why is it that the weakest force gets to have the grandest impact on the cosmos? That's a pretty cool question to think about. Thanks for joining us today.